My name is Ling. So today I want to explain about the task 1. In this first order system, we have to obtain the inverse Laplace transform, which is our equation is CT by assuming that A equals to 4 and B equals to 5, like this equation below. So in MATLAB, to plot the graph of CT, we have to open the M file to save the MATLAB code. Go to the home, then click the new script to open the script for code and write the code into the script window. Then choose a name for file and click to save. So in this code, we have to define the constant A and B equal to 4 and 5 accordingly, and define the time vector from 0 to 10 seconds with 0.01 second increment. And step 3 is compute the output equation CT like this. And the step 4 is add the title and access labels and legend, and use the x-states to mark the x-axis stakes at each integer from 0 to 10 seconds. After that, to plot the graph with B for blue color and line width to 1. So for the result, we have to get the graph like this. And we have to plot the x-axis and y-axis to obtain the output. So from this figure, we prove that all the calculation is similar to the hand draw graph. In this task 2b is a second order system. We have to assume the n equals to 4 and k equals to 1 for the transfer function cs over rs to determine the shape of graph. So in the MATLAB code, we also define the numerator and denominator gs first, and the second is set the time vector from 0 to 5 seconds with a 0.01 step size, and the 3 is plot setup. You have to, there's two colors, which are the blue and the red for the two gain values. And step 4 is SYS dash CL is used to create a closed loop system for uniting negative feedback like a transfer function above. So the step 5 is stimulate the unit step response. And the last two steps is to show the step info into command window by using the fprintf, and the last is add the title and exit label and legend in a figure like the red figure. So in this figure, we have to know that by comparing to both k equals to 2 and k equals to 1, the k equals to 2 has a more overshoot than the k equals to 1. It's not good for a system. So means that it is not stable like the k equals to 1 response system.
Task 2C, we are using Simulink in MATLAB to plot output response using different values of k, plot pole-zero map, and also consider disturbance in the system. As we can see here, this is our transfer function, TS, and we are using Simulink in MATLAB. As you can see here, we are using Simulink and type it in comment section. In second slide, we put the transfer function with different value of k in our block diagram in Simulink, and then we can come up with the pole-zero map. These are the setup. As you can see here, we put input for the pole-zero are the same, and the output is depend. We adjust the stop time for the scope, which is 100, and adjust the step time for the step component, which is 0.01. As you can see here, for the value k1, we can see here, for the value k4, and for the last one is the result of the step response graph. As you can see here, the red line is over them, which is k equal to 1. The blue one is k equal to 4, which is under them, and the yellow one is k equal to 8, which is under them. The red curve runs slowly and smoothly to the final without overshooting, so it is over them. So the blue line shows oscillation that gradually die out and settle at the final value, and the yellow line oscillate continuously with high amplitude and does not seem to settle down.
I'm Ku Xing, and for task 3, we already choose the rotational system as our system, and we already found the output equation and the state equation, and we also already initialized in the code. And for the A actually is the metric of this part, and B is metric in the T, this part for the state, and for the C is the output part, and is this metric, and D actually because our output we don't have the T right, so it's 0, and we're using the SS functions to find the set space model, and the TF functions to correct the transfer function. Like at here the window, after we're using this code and we're writing it out, it can give us the transfer function of GS. So we're getting the final answer, and after we're getting this final answer, we can using the Simulink to get the graph. And the Simulink how to open it is the same as the previous one, which at the task 2C. And so we already set out of it. Here's how to set up it. So we just like for transfer function, here we write the numerator and denominator that we get here. Then after we run it, we can get the result, and also the information of it. And for task 4, we already choose the water level control in the task as our project, and we already design it and get the function. And for this, actually, we try to get the better of the PID control. We already try to get the best, and so here's the best value that being gathered. And so we can start to do the MATLAB code. And here actually the step initialize and writing the numerator and the denominator, and we can using the TF to get the transfer function. And the step here, the step is to get the graph, and the step information is to get the performance specification. And for the pole-zero, we're using the PZ map to get the pole-zero. So after we run it, you can get all of this.